Hey folks, welcome back. In this video we're going to go over question 1 from the 2017 Specimen SQA National 5 Physics exam paper. So let's get into it. Question 1 says an aircraft is making a journey between two airports. A graph of the aircraft's velocity during takeoff is shown. So we've got a velocity time graph where there's a bit of constant velocity at the start and then a constant acceleration. Part A says calculate the acceleration of the aircraft during takeoff, and there's 3 marks available here. Well, looking back at the velocity time graph, the acceleration part starts at 5 seconds and goes up to 45 seconds, and that's the part we want to use to calculate the acceleration. So to calculate the acceleration, we're going to use the equation A equals v minus u over t, where the time is the time difference to go from 5 to 45 seconds, so that's going to be 40 seconds, just doing the 45 minus the 5. So our time is 40 seconds. Our initial velocity, you'll see, is actually at 5 meters per second, and then our final velocity v is at 55 meters per second. So writing all of that down, we have the acceleration is what we're trying to find, the initial velocity u is 5 meters per second, final velocity v is 55 meters per second, and the time t is 40 seconds. And writing down our equation that we mentioned, it's A equals v minus u over t, substituting in the numbers gives 55 minus 5 divided by 40, and putting that into your calculator should give you an answer of 1.25 meters per second squared. Or there's another way you could do this, which is calculating the gradient of the line, where you can choose 2 points on the line of best fit, plug them into your gradient equation m equals y2 minus y1 over x2 minus x1, and you should get exactly the same answer here. Part B says during flight the aircraft is travelling at a velocity of 150 meters per second due north and then encounters a crosswind of 40 meters per second due east. So we've got two velocity vectors here, 150 meters per second north and 40 meters per second east. It then says for part 1, by scale diagram or otherwise, determine the magnitude of the resultant velocity of the aircraft, and there's 2 marks available here. Well, we want to use either the scale diagram or the calculation method here. And looking back at our diagram, we want to take these two velocity vectors and add them nose to tail. So I'm going to bring the tail of this smaller vector and join it onto the nose of this longer vector to create a right angled triangle. So doing that, we have our first velocity vector, which we'll label A, and that's 150 meters per second. And then we've got our second velocity vector, which we can label B, and that's the 40 meters per second. We can then draw on our resultant vector, which goes from the start to the finish point, and we can put our double arrow on that to show it's the resultant to make it different from the individual vectors, and we can label that C. We can then show this as a right angle in here and label our angle theta, which is the angle next to the starting point. So here we're just trying to find the magnitude of the resultant velocity, which is the resultant vector. And we can use Pythagoras here, so we have c squared equals a squared plus b squared, and substituting in the numbers, that's equal to 150 squared plus 40 squared, and putting that into your calculator should give you 24,100. Now that's c squared, remember, so in order to get c we need to square root that, and that gives us 155 meters per second. Part 2 says by scale diagram or otherwise, determine the direction of the resultant velocity of the aircraft, and again there's 2 marks available here. Well, again we can use either the scale diagram or calculation method, and because we use the calculation method here, we might as well just keep using the calculation method. Now we can use the diagram that we sketched earlier to help us with this as well, because we're interested in the direction now, which will involve the angle theta. Now we always want to use tan theta for this, so we can say that tan theta equals opposite over adjacent, which in this case, opposite the angle is 40 and adjacent to the angle is 150. So we have 40 divided by 150, and to get theta on its own we can do inverse tan or shift tan on your calculator of 40 divided by 150, and that should give you an answer of 15 degrees. However, that's not our direction, that's just the angle theta here. Now to find our direction, we want to use compass points or bearings here. So using compass points, first of all, we know that this is north up here and this would be east over here. So our resultant vector is pointing at 15 degrees east of north. So we could say that's 15 degrees east of north for the direction, or if we want to write it as a bearing, remember we always start at north at 0, 0, 0, and then we move round until we get to the resultant vector. So that angle there is just the 15 degrees, but to write it as a bearing we need 3 digits, so we write 015, so it's a bearing of 015. Part C says the aircraft arrives at the destination airport. There are 3 runways X, Y and Z available for the aircraft to land on. The length of each runway is given in the table. So we have our 3 runways X, Y and Z and their lengths in meters. So we've got 3,776 for X, 3,048 for Y and 2,743 for Z. C part 1 says the speed time graph below shows the speed of the aircraft during landing on the runway from the moment the wheels touch down. So you see we start off at constant speed at 70 meters per second, and then we get this constant deceleration and then another constant speed once it reaches 10 meters per second. It then says determine which runways the aircraft could have used to land safely. Justify your answer by calculation, and there's 4 marks available here. Well, because we've got the lengths of these runways, we want to work out a distance travelled from this speed time graph. And in order to do that, remember, we need to calculate the area under the graph. So I'm going to start by splitting this graph into different shapes that we know the areas of. So remember, that's going to be rectangles and triangles. And it's got to be the entire area enclosed between the line and the x-axis. So let's split this area here into a rectangle first of all. So we'll put a line along there and a line down just to show that's our first rectangle, and we'll label that number 1 for our first area. You'll then see we've got this triangle shape here, so I'm going to draw a line down here to split that up and make it look like a triangle, and we could label that number 2, our second area. And then you'll see we've got this third area, this third rectangle in here, so I'm going to label that number 3 for our third area. So we've got 2 rectangles and a triangle that we want to calculate the area of. So we can start by saying that displacement or distance is equal to the area under our VT graph, and writing down our 3 areas, we have length times breadth plus a half times base times height plus length times breadth. So that's area 1, area 2 and area 3. And then we can substitute in our numbers. So for the first area, we have 70 for the length times 10 for the breadth, so that's 70 times 10. For the triangle here, we have a half times base times height, so that's a half times the base, which goes from 5 up to 50, so that's a half times 45 times the height of 10 up to 70, so that's a half times 45 times 60. And lastly, for the rectangle here, we have another length times breadth, so the length is 10 and the breadth is 60, going from 10 up to 70, so it's 10 times 60. So putting that all together gives us 70 times 10 plus a half times 45 times 60 plus 5 times 60. And lastly, putting that into your calculator should give you an answer of 2,350 metres. And now comparing our 2,350 metres to the lengths of these runways, because the lengths of these runways are greater, that means we could use any of these runways for the landing. So therefore, we can say runways X, Y and Z could have been used. Lastly, C part 2 says this airport has runways of different lengths to accommodate different sizes of aircraft. Explain why larger aircraft require a longer runway to land safely, and there's 2 marks available here. Well, we could say that larger aircraft have a greater mass, so therefore have a reduced deceleration. In other words, because the mass is greater, they're going to have a greater momentum, so it's going to be harder to stop them from moving. So a longer runway would accommodate that. Or you could say that larger aircraft have a greater kinetic energy, and since the work done EW equals the force times the distance, if the force F is constant, then the distance d is greater. In other words, because larger aircraft have more kinetic energy to begin with, more work is done to slow it down during the landing on the runway, and therefore the distance it needs to slow down is greater, so therefore a longer runway is needed. So where do your 2 marks come from here? Well, in the first statement you get your first mark for saying the larger aircraft have a greater mass, and your second mark comes from the part about having a reduced deceleration. In the second statement you're getting the first mark for saying that larger aircraft have a greater kinetic energy, and then the second mark comes from this second part here, talking about the work done and the distance being greater. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.